Hello, welcome back student to the next session in the unit 3 design and analysis of algorithm subject. So as we saw in the previous lecture, reliability design, and we saw the introduction to the backtracking. So if you did not watch the video, go and watch the previous video. So today we are going to see the Hamilton cycle. Today's objective is this, and in this, what is Hamilton cycle and what is the history and why it is included in your subject, that all the things we are going to see, why we need to do this, because as you know, the design and analysis of algorithm subject is purely based on the time complexity and the space complexity. Okay, so to reduce the time to solve the problem, we are using the Hamilton cycle. Okay, and how it is reducing and how it is working, we are going to see. Okay, so as I told you, in the backtracking we have different problems: 8 queen problems, graph coloring, Hamilton cycle, knapsack problem, 0 by 1 knapsack problem, sum of subset. Okay, but as per your syllabus, okay, we will complete the topics. So first, in today's session, we are going to see the Hamilton cycle. Okay, in this session, we are going to see the Hamilton cycle. So what is HC? Hamilton cycle is a cycle which passes once and exactly once through each vertex of G. So whenever we have a graph, in this graph, that should visit only the ones to each vertex. Hamilton path is a path which passes once and exactly once through each vertex of a graph. G can be direct digraph. So here in the graph, if we have a number of vertices, so Hamilton cycle is a cycle. In this, it should pass from all the vertices. Okay, and when we will say this is a Hamilton cycle, if it is starting from here, from the 1, so it should end with 1 only. Like here, this is a path. Okay, what is a path? 1 to 2, 2 to 3, 3 to 4 and 1. Starting from 1 and ending with 1. So this is called a Hamilton path. A graph is a Hamilton if and only if a Hamilton cycle exists. When the cycle is exist, means when we can make a cycle, then only we will get the Hamilton path, and we can say it is a Hamilton graph. Okay, so here it is invented by the Sir William Ron Hamilton in 1859 as a game. It is started as a game. Since 1936, some progress have been made, such a sufficient and necessary condition by given. Okay, so this is a small history about the Hamilton cycle. What was the Hamilton cycle? It is developed by the William Rowan Hamilton in 1859. Till 1936, it was not any progress. After that, it is in the progress and the sufficient or necessary the condition be given. Okay, what is the application for the Hamilton cycles? This Hamilton cycle is a fault random geometric network. In a network, if Hamilton cycle exists, the fault tolerance is better. Okay, in a network, if Hamilton cycle exists, the fault tolerant is better. So we can easily find if we have the Hamilton cycle, and our time complexity will also be reduced if we use the Hamilton cycle. So this is a graph. Two graphs are here, as you can see on the screen, G1 and G2. In the graph, G1 is having 1, 2, 3, 4, 5, 6, 7, 8. 8 nodes are there and all are connected. And this is called undirected graph. What we can say? Undirected graph. Because it does not have any arrow where it is going. We can go from 1 to 2 or 2 to 1. Okay. So this is undirected graph. Both are undirected graph. Now we need to check, is it a Hamilton or not? Okay, first we will see this, or we can see this also, no problem. So you can see, if I am starting from 1, okay, if I am starting from 1 to 2, I can go. From 2 to 8, 8 to 7, 7 to 6, 6 to 5, 5 to 4, 4 to 3, 3 to 1. So from where I am starting, I am reaching the same position after visiting all the adjacent vertices. Okay, after visiting all the vertices, we are reaching to the 1. So this is Hamilton cycle, G1. Okay, and what is the root? 1 first, 1, what is the root? Sorry, 1, 2, 3, from here to here, then here, here, from here, going to 1. Okay, from 1 to 2, 2 to 8, 8 to 7, 7 to 6, 6 to 5, 5 to 4, 4 to 3, 3 to 1. Okay, so this is a path, and this is a Hamilton cycle. Cycle is also happening, and we are getting the path. Let's check it out. This cycle, I am starting from 1, okay, 1 to 2, 2 to 3, 3 to 4. Then again I cannot visit the same vertices. Which vertices is visited once? So here I am stopping. I could not able to reach here to the 1. Okay, if I go from here 1 to 2, 1 to 5, 5 to 2, 2 to 4, 4 to 3. But I can't reach the 1. So this is also not possible of Hamilton cycle. So this is not a Hamilton cycle, and this is a Hamilton cycle. So we can check all the possibilities, and we need to find which one is a Hamilton cycle. Okay, next, as I told you in the previous slide, graph G1 contains the Hamilton cycle, and the path are here. Mistake is there. Okay, what is the mistake? 1 to 2, 2 to 8, 8 to 7, 7 to 6, 6 to 5, 5 to 4, 4 to 3, 3 to 1. So this is a path. 1, 2, 8, 7, 6, 5, 4, 3, 1. Okay, so this is a Hamilton path. Graph 2 contain no Hamilton cycle. Okay, as we saw just now. Here solution vector x1, x2, so on xn is defined so that xi represent the I vertices, visited vertices of proposed cycle. The graph is started by the initializing adjacent matrix. Whenever you are going for the Hamilton cycle, you must see the adjacent matrix, means which vertex is near to the visited vertices, it will select that. Okay, so 1 to n, n1 to n, then string setting x2 of n to 0 and x of 1 to 1, then executing Hamilton 2. Okay, this is a thing regarding the Hamilton cycle. Okay, if I take the example any example for making a tree. Okay, like example, if I am taking, sorry, A, I will increase the font. Here I will increase the font. Okay, here if I take, we'll take this one, A, okay, D, B, C, E, F. So I am taking the graph, undirected graph, and this all are the connected. Okay, and here this is a graph, and for this, if we need to check whether the given number, given graph is a Hamilton cycle or not, for that we need to make a tree. We need to make a tree. Okay, okay, fine. A to B, B to C, C to D, E, F. This all are connected in the graph, and now this is also connected. Okay, now I need to make a tree. I need to make a tree like A. Okay, otherwise I will make a small one. A, and how many are there? From A, it is going to B, going to C, is going to D. 1, 2, 3. 3 connections are there. Okay, A to B, C, and D. From A to B, A to C, A to D. Okay, now you can select any one of this. So I am selecting the B one. From the B, I can go to A, I can go to C, I can go to F. So already A is visited, so we no need to go with this. B to C and B to F. Okay, B to F. Now, in the same way, we need to do for the C. From the C, in the graph, I can go to A, I can go to D. Okay, from C to D, I can go to B, I can go to F. Okay, I can go to F, as well as I can go to E. Okay, so the 4 possibilities for the C. Okay, now next, for this D, I will erase and increase the, this is D. Okay, and here from the D I can go to C. Okay, from the D, this is a D. From the D I can go to C, I can go to A, I can go to, not anywhere, only C. Okay, now from here A is, I am closing because it is a dead, we cannot go further. If we go to A, then again I am going elaborating this tree. From the C, where I can go to the B, I can go to the F, I can go to the E, but already the B I already visited. Okay, already I visited the B, so no need to go there. So from the C I can go to the E and F, as well as this D. Okay, from the C I can go to the D, I can go to the E, I can go to the F. Okay, now but D is a dead state because it's again coming to the C as well as the A. So for that reason we are telling this is a dead state. We cannot go. This is not a Hamilton cycle if we go in this way. Next, from the E I can go to the C, I can go to the F. So already E is here, so already C is completed, so we no need to visit that, directly we can take the F. Okay, next, from the F, where I can go from the F, I can go to the C and B. So already B and C is finished, so last one is remaining is E. Okay, so after F is E, so already is here, so this is also I am deading, means here it is stopping. We cannot go further here while seeing this diagram. While seeing this graph, we cannot continue. Here we are deading. We are not getting the success node. Okay. From the F, I can go to the B, I can go to the C, I can go to the E. But here already we completed the B, so we can go to from C and can go to the C as well as E. E and E. Okay. Now from the C, where can I go? From the C, I can go to the D, I can go to the D, I can go to the B, I can go to the E, and it is coming from F. So we need to remove this F. So what we need to write here? E and D. These two, E and D. B and F is already in the same list. Okay, fine. The next one, from the E, where it will go? From the E, it will go to the F. Already F is here. Okay, and it will go to the, it is not possible to go anywhere with the help of E. C, E, D. From the E, we cannot go to the C, cannot go to the F, we cannot go to the, so here stopping. From the, sorry, from the D also it is not possible. Okay, next, E. From the E we can go to the C and F. Already we are coming from the F, so we can go to the C. Can go to the C. Okay, from the C, where can I go? Can I go to the D? Yes, and D is not in this list. From D. Okay, from the D, can I go to the 1? Yes, it's possible. So we got the 1. 1 success. 1 what is the thing we got it here? With the help of tree, we got this success. So this is a Hamilton cycle. Okay, A, B, F, E, E. If we go the route like this, then the last we can reach to A. Okay, last we can reach to A, B, F. What is the route here? From A to B, E to F, F to E to C to D, D to E. Okay, it is going like this. If we go like this, then it will become a Hamilton cycle. The rest of the graph we can make, we can check. Okay, like D we cannot reach. From the B, from the given graph, from B I can go to C and F and A. So, already we completed the C. Then we possibility to go F. Okay, we have a possibility to go F. Okay, from the B, F, E. Okay, so here after doing this, C is E, E to F, F to D. As per the graph, if we go like this, there is a possibility from F to C to F. As per the graph, B, sorry, B and C. Okay, so here it is not possible, it is not possible. So let's check it out this. From A to D, E to C, C to E, E to F, F to B. All 6 vertices are reaching here, and this is a path for the Hamilton. This is a path for Hamilton. The rest of the paths are not Hamilton. Okay, cross all the cross, because this is a not reaching to the A. Okay, so we got the 2 successive. So what is a Hamilton path here with this graph? Okay, so I will write the path for this. Here I will write. Okay, so what is the path now here? It's going, 2 possibilities are there here. 2 possibilities. First one is from A to B, from B to F, A to B, B to F, from F to E, from E to C, from C to, from D to A last. So we can, is it a possibility to go from here? Okay, next. Second one, starting from A, and it will be D, then it will be C, then it will be E, D, F, B, and the last A. So you remember this, if your Hamilton cycle, okay, if your Hamilton cycle is there, so definitely you will get the 2 success node at least. If it is Hamilton, then you will get the 2 success node. like C, A, B, F, E, C, D, A, then again read the reverse, you will get the second one. A, D, C, E, F, B, A. A, D, C, F, B. Whatever the answer you are getting, any one of this, then you need to read from the right to left. Then you will get the answer. Okay. So here, this is a Hamilton cycle example. And what is the time complexity for this? Is order of n power n. Okay. Order of n power next. In the Hamilton cycle, we have a different graphs are there. That graph are the Hamilton cycle or not, you need to check. Okay. So here we will see the algorithm now. What we are doing in the problem, we are checking the nearest, means adjacent vertex and visiting that. Okay. So algorithm, you need to write in the exam algorithm Hamilton k repeating next to value k. If x of k is equals to 0, then return x of 1 is to n. If k double equal to n, then Hamilton k plus 1 until it will false. Like if you see the here, what we are doing here actually, like example, we are using the backtracking here, and when we are reaching here A, if it is not a success, so what we are doing, we are going back. This is called backtracking, brute force attack. Again it is coming to C and checking, then here also it not possible, again it will go back. Okay, if it is not possible, go back. So it is a backtracking technique using to solve the Hamilton cycle. Okay. Next is next value. Okay, this is the Hamilton k and repeat next value k. So what is the next value k? Repeat. So this is an algorithm. Okay, x of k is equals to x of k plus 1 mod n plus 1. If x of k is equals to 0, then break if g of x k minus 1 comma x of k does not equal to 0, then 2k minus 1 do. If x of j is equals to xk, then break. If j double equal to k, then k less than n or k is equals to n. This is g of x of n, x of 1 does not equal to 0. Then return. Okay. So when we do this algorithm, so whatever the operation we perform till now in the graph while using the tree, that you can write in this algorithm. Okay. So Hamilton will find the minimum cost tour if a tour exists. Means if the tour is exists, then it will find the minimum. Like in the graph from, if it is given some number, example here 4, 5, 10, something like that. Okay, so it will cost, based on the cost we can get the minimum cost. If the h cost is c, then cost of the tour is cn, since there are n edges in a Hamilton cycle. We don't know how many edges are there. Okay, if the 8 vertices are there, then it will be a possibility minimum we will have a 7 vertices. Sorry, if we have a 8 vertices, then minimum we will have the 7 edges. but here we don't know how many edges are there, so based on that situation it will calculate the cost. The develop such an algorithm for Hamilton cycle which is more efficient in terms of time complexity. Okay, so the summary is we completed the Hamilton cycle. While taking the example also we completed and we saw the algorithm. Okay, in the next class we are going to see the other topic from this given list. Okay, so today we completed the Hamilton cycle. This is we completed. The next class we will see the graph coloring. Okay, where it can be used we'll see. Thank you very much. We'll see you in the next class.